All right, we all set with the video? All right, why don't we go ahead and get started? So welcome back, everybody, to EE240. Just a couple of sort of administrative things before we get going. As I'm sure you guys all remember, homework is due this Thursday. Just drop that off in the box outside my office. Pierluigi will pick that up basically 5 p.m. sharp, so don't be late on that. How many of you guys actually finished already, by the way? One problem left? Didn't even start? Hopefully no one will raise their hand. Okay, good. So certainly keep that in mind. That's coming up fairly quickly here. I'll have his office hours today. Pierluigi has office hours tomorrow. The other sort of reminder is I'm actually going to be out of town this Thursday. So we're taping ahead the lecture this afternoon. So that'll be 3:30 just over here in Dwinell. Again, I realize that some of you have 241 at that time, but for those of you who don't, please do show up. You know, it's much better when I'm talking to people rather than talking to the walls. So if you can, please do be here. The other sort of reminder, which anecdotally means we're going to have somewhat of a long quote-unquote break, is that next week is actually ISSEC, which means we're not holding any lectures. So today is kind of the last lecture for about a week and a half or so. That's not to say you should slack off. There will be a new homework that we'll be posting. It'll be covering some of the stuff that we'll be getting into today. If not this lecture, then later this afternoon, mainly dealing with actually noise, so be on the lookout for that. There won't be any office hours from me on the ICC week. I have to talk with Pierluigi. I'll see if he's going to hold maybe something on that Wednesday. I don't expect that there'll be too many questions, given that most of you will also be at the conference, but definitely if anything comes up, just feel free to shoot us an email and let us know. So any questions on logistics or material or anything like that so far? Yeah.
Since we don't have lecture on Thursday, where do we turn in our homework?
Oh, so I just mentioned just turn it in the box outside of my office. Okay. In general, that's what you'll always do. If you give me the homework, then there's a good chance that I may somehow not take it back. So just put it in the box outside my office. Any other questions on logistics or material or anything like that? Yeah.
Usually, what time do you check that box?
It's going to be 4:59 and 59 seconds. How's that? Precisely on the dot from I don't know, Big Ben or whatever. Obviously, don't push it because we will be checking that basically on time. So get it in at the right time. Does that answer your question? Or okay. Other questions?
We just had a class last year where they check their box at 8 a.m.
No. So I think I explicitly say it's 5 p.m. on the day it's due. So it's always 5 p.m. the day it's due. Okay, so with that, maybe we can go ahead and sort of launch back in. So last time we had sort of started talking about, we had all these sort of large signal models. We talked about how they were a pain in the butt. There was all these weird effects. We couldn't really come up with a great sort of analytical way of dealing with things. So we said that what we started kind of wanting to do was really just look at, from a small signal design standpoint, what is it we really care about? And where we basically ended up was looking at this so-called efficiency parameter called GM over ID, or just, I should say, defined as GM over ID. And what we said was kind of interesting about that parameter is essentially it tells you if I want to get a certain transconductance, which as we'll see in a second is pretty easy to calculate usually, how much transconductance you actually need. This parameter basically tells you how much bias current you have to spend in order to get that amount of transconductance. Okay? So what we looked at is if we had a, let's say, long channel MOSFET, meaning something that behaved quadratically, then it was really easy to basically figure out that that GM over ID was just directly related to 1 over the overdrive, or the VD-SAT, as sometimes we like to call that. Whereas an example, let's say in a BJT, that GM over ID was related to 1 over the thermal voltage. And where we basically ended up was saying something like, well, in a MOSFET, if you want the thing to be saturated, you need, let's say, 100, 200 millivolts of gate overdrive, right? And so the sort of GM over ID you can get from a MOSFET, that's usually what sort of people complain about. That GM over ID was worse than what you could get from a BJT. Now, as we also talked about, if I basically dropped the VGS on that MOSFET far enough down, it starts looking like a BJT just because it's in the subthreshold region. That's kind of what it is. And then the GM over ID you get kind of approaches the same as what you would be able to get from a BJT. With the only quote-unquote minor issue, of course, that because you're actually not directly controlling the base, but rather controlling it through a capacitive divider, right? So it kind of looks something like that. You don't exactly get that 40 inverse volts of GM over ID. You get something about 1.3 times smaller than that. So you can see here about maybe 25 or something in that range. Okay? Now what's interesting is notice here that from this standpoint, actually, particularly over here on this region of the curve, NMOS and PMOS devices don't actually look very different in terms of their GM over ID characteristics. So by the way, what do they look different in terms of? So obviously this parameter is not all that different, but what is going to end up looking a little bit different, which we sort of hinted at a little bit last time. What is really going to be the difference between NMOS and PMOS?
Resistance.
Resistance. Okay, what do you mean by that? So remember, I'm an analog guy. So if I want to get, let's say, a certain GM, and let's say I bias both my NMOS and my PMOS right around here. So looks like the bias current I need is about the same, right? What's different?
The FT?
Yeah, the FT is different, right? In other words, the parasitic capacitance I'm going to have to get that GM is going to be different. To say it another way, the PMOS is going to have to be wider to get this same, basically the same GM over ID, right? And so in fact, for those of you guys who have done the homework and will see why we set it up that particular way, that's why I asked you to plot some parameter related to GM over ID. We'll go over what that parameter is in 1 second. And basically the amount of current you get per unit width. Because that's really what you're going to be using to figure out, okay, how much parasitics am I going to be introducing from a given device if I bias it at a certain GM over ID, okay? So what I've kind of been driving at this whole time is this GM over ID or current efficiency sort of looks interesting perhaps as a something that we might want to use from a design standpoint, okay? And there's kind of one really key thing here, which is that even though there's all kinds of these nasty effects I talked about last time, I can always determine exactly what GM over ID is, right? Because either in SPICE or just if I have the device itself, I can always just take the measurement, plot that IV curve, measure the ID, measure the slope of the curve, and then I can literally just do GM over ID. Doesn't matter if there's short channel effects or whatever weird quantum, whatever it is, I can always do that, right? So I can always measure this GM over ID. That's why it kind of looks attractive to us from a small signal design standpoint. Now, the units of that are, again, a little bit weird. It's inverse volts. And so it's sometimes a little bit hard to kind of physically interpret what that actually means. But we're just going to redefine things in an essentially equivalent manner to take care of that in 1 second. Okay, but bottom line, I'm really interested in doing this because, again, if I can just basically decide what GM over ID I want, independent of all the short channel effects and things like that, I can just basically use SPICE as a lookup table and figure out what's the mapping from that design thing that I know I want to the actual transistors that I'm going to end up building. Okay? So let's just see how we're really going to do that. So rather than looking at GM over ID, which again has this kind of weird units, which is inverse volts, instead what I'm going to do is just define a new parameter. That parameter, I'm just going to call it V star. Okay? Now this V star, again, has no physical meaning other than just I've defined it exactly this way. I'm just defining it as 2ID over GM. Okay? Now, why did I pick this particular definition? Well, if you kind of pay attention, what that means is that if I really did have a quadratic device, meaning a square law device, then this V star would be exactly identical to VGS minus VT, or VD-SAT, okay? So that's kind of nice because it means, if I had a square law device, I really could just replace VGS minus VT with V star. I'd know exactly what that means from a GM over ID standpoint. But keep in mind, I'm just defining this V star this way, even though real devices are not at all square law, okay? So why am I doing this? Well, because even though they're not square law, a lot of the intuition that we have about what happens as you change VGS minus VT is also sort of similar to what happens if you change V star. It's just that there isn't that one-to-one mapping between V star and the actual VGS minus VT you're going to use, given that the device has all these weird characteristics. Okay? So again, maybe just as a reminder, I know we talked about this a little bit last time, but if you change VGS minus VT, what things in your circuit does that kind of impact that you care about as a designer? Other than obviously the GM over ID. What else does that impact?
Swing.
Yeah, it impacts the swing because it has something to do with how much drain voltage you can put across the device before the RO gets bad. What else does it have to do with that we just talked about? Why don't you generally want to use like 0 VGS minus VT, or even negative for that matter? We usually complain about.
Speed.
Yeah, it's slow, right? So in other words, smaller VGS minus VT, or in other words, smaller V star, is going to translate into larger parasitics, right? Because I'm basically going to have a bigger device for the same unit GM, okay? So that's really kind of the key here, is to keep in mind all the stuff that we know about V overdrive. You can kind of wave your hands a little bit and apply to V star, okay? Now, again, it's not that the mapping is exact. It's just the intuition holds. So just like we said, you know, with V overdrive, for long channel devices, there's all kinds of, you know, nice things we know about it, right? So V overdrive is the voltage at which the device comes out of saturation. It also happens to be equal to V star. We know that the drain current is proportional to that overdrive squared, right? The RO is sort of large for VDS greater than V star. And again, as we just said, basically the device parasitics for a given unit current change as we change that VOD. Okay, so all these things kind of, by analogy, kind of hold or are similar as we change V star. It's just that remember, it's not exact because the devices don't really behave the way that quadratic devices sort of would imply. So again, the other sort of nice thing about doing this V-star methodology is if I really had a short channel device, in fact, even if I had a long channel device, there's no direct way for me to measure VGS minus VTH. Because I can't actually, by the way, how many of you guys have ever tried to measure the threshold of a MOSFET, either in SPICE or in the lab? Somebody must have given you that homework at some point. Okay, well, I know that somebody in this class gave you that homework through SPICE by, you know, doing .lx whatever. So, you know, there's a bunch of people that didn't raise their hands. Do you guys just not do that homework yet, or what? Okay, well, so if you didn't have that magic, you know, thing that you can grab out of SPICE that says the threshold is blah, actually measuring the threshold is pretty tricky. And in fact, by the way, there's all kinds of different definitions for what the threshold really is. Because remember, it's not that magically the current goes to 0 at that threshold. It kind of, you know, the IV curve, let's say, does something like that. So how do you decide really what the threshold is? Okay? Point here being that even if I had the device handy, I can't measure that VGS minus VTH. Whereas this, again, ID over GM, or that V star, that I can definitely measure. And certainly I can simulate it very, very easily. Okay? So no matter what the device is, even if it gets out all kinds of horrible, complicated equations, I can always pick off what that V star actually is. So basically from now on, what we're going to do is, even though we have these short channel devices, we're basically going to work with this V star, which again is just defined as 2ID over GM. Okay, we're going to work with that V star, pretend that it's kind of like our overdrive, but whenever we really need to map to real device parameters, we're just going to use SPICE as a lookup table. Okay? So the best way to really see sort of how all this works is to go through a design example. Okay? So all I'm really doing here is just building a common source amplifier. So this is kind of the circuit that I'm interested in. All this stuff that's on the left over here, that's just to bias the circuit up at some nominal DC point that we're interested in. Okay? So all I've done is I've taken some bias current, which I'm going to calculate what that bias current needs to be in a second. I'm essentially tying this transistor up almost like in a diode connected configuration. Just that I put this op amp in here so that, again, I can control the nominal drain voltage at the output. This is a very similar trick to what we had shown maybe a lecture ago in terms of how we could measure the RO as a function of VDS. Okay? So this whole thing, again, that's just to set some nominal gate voltage over here to bias this transistor up, which is really my amplifier. And then I'm going to put this voltage source. That's kind of my input voltage. Okay, so that's like the small signal voltage that I'm dealing with. So now, let's see how I can use this V star to really quickly come up with what I claim is basically an optimal amplifier design. Okay? So first, of course, we need some specs that we're targeting. So let's just say that I want my small signal open loop gain to be greater than 70 across some voltage swing. So I'll tell you what that voltage swing is in a second, but let's just assume that I told you what that voltage swing was. Okay? I'm also going to tell you that I want the gain bandwidth of the amplifier to be 100 megahertz. In other words, the unity gain point should be 100 megahertz, where I'm driving a capacitive load of 5 picofarads. Okay, I've just come up with these numbers. Let's pretend that that's what you want to do. We'll talk a whole lot more later about how you would come up with those numbers. But let's just pretend that's my specs. Okay, well, first step is, basically, if I want to hit this gain parameter here, at least with this particular topology, there actually isn't a whole ton of freedom in some sense. Because really all I have to play with is kind of the sizing of this device and how much bias current is flowing there. So usually the first step you actually are going to take is just, you remember I said you want to generate these plots that show you what's the open loop gain as a function of the voltage and at different channel lengths? Well, basically first thing you're going to do is just take a look at this open loop gain number and then see, okay, for the swing that I'm targeting, what's the minimum channel length I need to actually hit that open loop gain with that swing spec? Once I've done that, I just go, I look in my tables, I find the shortest length I've got that'll do this. I pick that length. Okay, that's it. So in this particular, this is a totally different technology than yours, by the way, but in this particular technology example that I used, turns out that a channel length of 0.35 microns is what I need to hit this gain of 70 spec. Okay? So from the standpoint of length, I'm done. I've chosen whatever length I need. Now, by the way, why is it I always want to choose the shortest length that I can? Any thoughts on that? Why don't I always choose like really long length?
You'll burn less current for the same bandwidth.
Ah, there we go. It's basically bandwidth, right? And we'll talk about that more in a second. But if I always used a really long channel length, and I didn't actually need that much gain, for the same bandwidth or really for the same parasitics, I'm burning more current than I really need to. Okay? That's exactly right. All right, so I know my channel length. That's fixed. What's next? Well, I just have to figure out how much GM do I need. So just as a reminder, the equation is sort of implicitly written there, but what actually sets the unity gain bandwidth of an open loop amplifier like this? What's that set by?
GM over CL.
Yeah, it's just GM over C, right? And really, just as a really quick reminder, just in case you guys forgot this somehow, if I have a common source amplifier with a resistive load, so let's call that CL, we'll call that RL. Of course, what's the pole associated with that?
RC, 1 over RC.
Yeah, 1 over RLCL. Okay, what's the DC gain? GMRL, right? Okay, so if I want the unity gain bandwidth, then it's just ADC times the pole, and then of course you get GM over CL. Okay, keep that one in mind because it pops up all over the frickin' place, so just know that one cold. Okay? And yes, indeed, it doesn't depend on the load resistance because all the load resistance does is moves around both the gain and the bandwidth. Just like, hopefully you remembered from way back in one of your very first courses about, op amps and feedback and stuff like that. Resistance doesn't actually change the gain bandwidth. Okay? So, if if the gain bandwidth or the unity gain frequency is just GM over CL, and I've told you that I want 100 megahertz of unity gain frequency, then all I have to do is I have to say that GM is equal to CL times 2 pi and that unity gain frequency, right? Which is exactly what I wrote right here. So if I take the numbers that I gave you here, so 5 picofarads and 100 megahertz, you can really quickly calculate, I need a GM of 3.14 millisiemens. Okay, so now, next step in my sort of design procedure, I already know the channel length. What's sort of left is to pick the bias current and the width of the device. So in order to do that, here's where I'm sort of going to pull out a little bit of magic. I'm just going to decide, well, as a circuit designer, and I'll motivate how this is in a second, I know that roughly speaking, for this particular technology and this particular frequency, I think I want about a V star of 200 millivolts. Okay, again, I'll explain the magic of where I came up with that number in a second. There's, of course, no real magic there. It's not all that difficult. Bottom line, let's just pretend I choose a V star of 200 millivolts, because I know that that's roughly the right thing to do. Well, guess what? As soon as I've chosen that V star, the bias current is completely specified. Because I know GM, and picking V star is exactly equivalent to taking the relationship between GM and ID. Okay? So just in case it's not clear how I got there, remember V star is 2ID. Oh, oops, excuse me. I usually do it the other way. GM is 2ID over V star. So if I've picked V star and I know GM, you can calculate exactly ID by doing that. And by the way, it just so happens, V star of 200 millivolts is a 10-to-1 relationship between current and transconductance. So in other words, if I want 3.14 millisiemens, that takes me 314 microamps. And I just mentioned it because that's a good number to remember, because when you're doing these kind of calculations quickly in the back of your head, you know, that factor of 10 is really nice and easy to take care of. Okay? So I now know the bias current, I know the length, I've hit, hopefully, my frequency spec. So really the only thing that's left, which again I actually kind of claim that from a design standpoint maybe is not really what you cared about, but obviously eventually you have to specify, is how big am I actually going to make the device? Because I already know the bias current, I already know the GM I want. Really all that's left is how big is the device itself. Well, so to do that, since I've already picked my length and I've already picked my V star, and I know sort of how much GM I want, really all that's left is for me to figure out at that given V star, how much current per unit width does my transistor give me, right? And by the way, this is exactly why I asked you to do this in your homework. Because from now on, whenever you're doing a design, if you say you want a V star of 200 millivolts, you can say, okay, that gives me, let's say in this case, I don't know, whatever it ends up being, 120 something odd microamps per micron. So now in this particular case, since I know I actually want 314 microamps to get my GM, the way I find the size is trivial. I just figure out, okay, 314 microamps divided by, okay, it was 141, so I got it a little bit wrong. 314 microamps divided by the 141 microamps per micron tells me that, oh, is that right? Oh, no, sorry, this is not actually microamps per micron, it's microamps per 10 microns, excuse me. Okay, so in your homework, I gave it to you as microamps per micron, or I told you to do it for a 1 micron device, because that's usually what I remember. This particular plot here used 10 microns, that's why there's the discrepancy there, okay? But again, bottom line, once you know the current density, you just say, how much current do I need, divided by the current density for the device at that V star. That's the width I need, okay? Yeah, question in the back? So what would not work? So where is anything that I've done broken from the standpoint of short channel? Or I should say maybe, is anything broken from the standpoint of short channel?
ID equals point.
Say that again.
That equals GM V star over 2.
Remember, I defined V star as being 2ID over GM. Right? So
But that V star is not overdrive anymore.
it's not overdrive, exactly. That's the whole trick. So this plot that I've gotten here, it's literally a lookup table from Spice. It's taking into account all the horrible nonlinear junk and everything that's happening in the device, simply by me saying, I knew I wanted a V star of 200 millivolts. So it actually works beautifully well for, I claim, any technology. Okay? Now, again, the trick I had to play was I said it's V star. It's not V overdrive. So if I were to say the device is out of saturation as soon as VDS is less than V star, that's out the window. But from the standpoint of just getting the bias current, the width, everything, this is actually dead on. Simply kind of by definition almost, by the way. Does this make sense to everybody? Or? So from now on, and again, by the way, this is why I had you do these plots. This plot right here is probably one of the most important plots. Obviously, there's several of them for different devices. That's probably one of the plots you're going to be using the most in this class. It's really going to tell you, okay, for a given V star, what's the current density from that device? Once I know that, I can really, really quickly calculate device widths based on how much GM I actually need. So does this make sense to everybody? Yeah.
If we're only doing this for a few lengths, then we should just interpolate between, or?
Yeah. So you could generate, a whole bunch of additional plots. In fact, I guess if you were really motivated, you could write a little script that would go and say, okay, I've given you the gain spec, so let me go and find exactly the link that gives me that gain spec, and now let me generate the V star. So you could do all that. The good and the bad news is it's probably not going to buy you that much. And maybe, again, the good and the bad news is in a lot of the newer technologies, you're not even actually allowed to do that. You're only allowed to use 3 or 4 discrete different channel lengths. Okay. It has to do with lithographic issues. You probably, maybe not right away in school, but by the time you get out, you'll probably be dealing with that kind of stuff. So you're right. It's a little bit, you have to interpolate a little bit, but usually when you're down to that last 5-10%, I kind of claim don't bother spending your time because there's probably another order of magnitude somewhere that was more important to go after. But you're right. Yeah.
So in this case, I don't care the physics at all. I just generate a manual plot. And
bingo. Yeah, so there's no physics behind it other than just whatever the heck Spice or the device itself is saying is going on behind it. Now, obviously that does mean there's several of these plots because there's different process corners, there's different variations in the device. So you as a designer, when you pick this V star, you should be careful to pick it at the right corner or really understand what are the variations that could be happening, and so make sure you have some margin in there. But you're absolutely right. There's no physics behind why the curve looks this particular shape. That's just taken as a given from the device. And now again, there's going to be a little bit of physics we're going to use, or maybe a little bit of intuition we're going to use later on to decide how in the heck I came up with this 200 millivolts V star. But, give me 10, 15 minutes, I'll tell you where that came from. Okay? Any other questions on this? Yeah.
I want to implement this 22 micron. So I wouldn't put one device of 22
We'll
micron.
talk about that in 1 second. Okay, well, yes, you wouldn't do that. We'll talk about that in 1 second. Okay, so since I sold this so hard, maybe, it won't be any surprise to anybody, but if I actually followed this methodology, it basically works dead on. Okay, because I picked the device from the get-go to give me the gain spec I want, and let's just pretend that I told you from the get-go that I wanted the swing of plus minus 0.45 volts, so I met my spec, again, kind of by definition. And the other thing, which usually, probably you were sort of really frustrated by, maybe in 140 or some other class, I've gotten the gain bandwidth essentially dead on. And again, the way that I did that was really almost by definition, because I know exactly what GM I need, I know what the load cap is, so just by looking up the device parameters, I've guaranteed that I really got that GM. Now, it's, when I said it's dead on, I did cheat a little bit here, because I picked a load capacitance that was large enough, and a V star that was kind of good enough, quote unquote. I'll quantify what I mean by that in a second. that I knew that any parasitics I was introducing from the device would be kind of small relative to that load cap. And that's why I really got this kind of dead on. Obviously, if I'd chosen something else for V star, if I'd chosen something really stupid, that wouldn't have actually happened. I would have had some drain cap from the transistor itself, and if that was large in comparison to the load cap, I wouldn't have gotten this right. So now the next question we need to sort of spend a little bit of time on is, okay, how did you come up with 200 millivolts? Why didn't I choose, for example, 75 millivolts, or which, by the way, is really, really close to subthreshold, if not in subthreshold, or even try and push it all the way down to, let's say, the absolute minimum you can get, which is probably not that much lower than that. Probably like, I don't know, 55, 60 millivolts or so. Okay, so in order to understand why I didn't choose this, or how I chose really this 200 millivolts in the first place, let's take a look at the AC model for the devices. Because everything we've been talking about so far, we've hinted at dynamics, but has really been purely DC based. So again, this is just sort of a quick reminder from, let's say, 140 or one of your other analog circuits classes. I'm going to do the small signal AC model. I just have to include sort of all of the standard capacitors. So of course, from the gate side, you're going to have some CGD. You're going to have some CGS. And don't forget, there's also actually some CGB, right? These are usually referred to as the intrinsic capacitors. Okay, they're called intrinsic because they're sort of fundamental to a MOSFET. Right? It's called a MOSFET because there's that metal oxide semiconductor that has capacitance. All these caps are intrinsic to the behavior of the device. Okay? That's not to say, of course, that you should forget about the so-called extrinsic capacitors. So things like drain to bulk or source to bulk. These are the things obviously sort of associated with the junctions. Again, they're usually called extrinsic. They're called extrinsic just because they're there, but they're sort of like, they're associated with stuff around the sort of core of the transistor. Okay? So, but, you know, hopefully, again, I'm sure you guys have seen this a bazillion times, so this is mostly meant to be a reminder. So that's our sort of small signal AC model, at least for the NMOS device. Now, of course, if we do this for the PMOS device, it basically looks the same. So just like before, we've got a CGS, we've got a CGD, we've got a CSB, we've got a CDB, we've got a CGB. But there's, of course, some additional cap here that we usually like to forget about, which I had mentioned before, and SPICE, of course, has nothing built in to handle, which is, of course, there's also going to be a C body to substrate. Okay, and again, that's just, that's hard to see. Let me change the color there. That's just the capacitance, basically from the well to the substrate. Okay? Again, if you have some really sensitive circuit, don't forget about that, because that may actually come into the picture. But otherwise, small signal-wise, model for the PMOS, basically same as the NMOS. Okay, so now, one other thing that I need to sort of briefly mention, because I'm sure it's bugged the heck out of you if you ever actually looked inside of the printout that HSPICE gives you. If you actually try and do a real model for a device, you have to be very careful to remember, what does capacitance actually mean? So, by the way, just what is capacitance really defined as? Anybody remember? Okay, so you said Q equals CV. What if I have a nonlinear capacitance?
dq over dv.
There we go. So capacitance is, by definition, the change in charge for a certain change in voltage. Okay, so for a linear cap, indeed, Q equals CV. But unfortunately, basically none of the caps in a MOSFET are really linear. Okay? So the reason I bring this up is, notice that that voltage can actually be any one of a number of different voltages. Because in a MOSFET, I've actually got 4 different terminals, right? I've got the gate, the source, the drain, and the body. So not only do I have 4 different terminals, which of course means I can define 3 independent voltages. By the way, remember, voltages are always relative. That's why it's 3, not 4. Okay? So I can define 3 independent voltages. And I can also define charge at each one of the terminals. Okay? So if you kind of work that out, what that tells you, there's actually 9 different derivatives. Okay? Those 9 different derivatives are essentially how much charge do I get at a given terminal, or how much change in charge do I get at a given terminal for a given change in voltage. Okay? Where that voltage is one of those 3 independent voltages. Now, why does this get really confusing usually pretty quickly? How many of you guys have ever actually looked at the printout that SPICE gives you if you do like a .op or a .ac and looked at the parameters associated with a given MOSFET? Anybody ever done that? Only 1 or 2 people? You guys never actually look at the printout SPICE gives you? Okay, well, you're going to be doing that. I'll strongly encourage you to do that. So if you ever did that, you probably saw something like it reported you not only just CGS, it also reported CSG. In fact, what might have really confused you is it would report not only CGD, it might have also reported CDG, and one of them might have been negative. Okay? So what's going on here, this is again the only reason I mention this, is that what's really going on is in order for SPICE to actually get things right as a simulator, it actually has to use this. Okay? So what these things mean, what CGS or CSG actually means, is the notation is basically as I've shown here. So that I, or the first thing, and let's take CGS. What CGS means is the change in charge at the gate given a change in voltage at the source. Okay? Similarly, if I have CSG, that's the change in charge at the source given a change in voltage at the gate. Now, intuitively, we like to think of those two as kind of being the same, but it doesn't necessarily have to be. Okay? And in particular, for CGD or CDG, that certainly it doesn't have to be the case. And the way to see that is just remember, if you change the drain voltage, that doesn't really very much change the channel charge, right? Whereas if I change the gate voltage, that is going to change the channel charge, and some of that's going to show up at the drain. Okay, so that's why you can get these kind of weird asymmetries and things that intuitively just sound very strange to us. Okay? Now, it's not that I expect you to actually go and worry that much about this when you're doing designs. It's just that you need to know about it because when you want to actually interpret the data SPICE gives you, you need to understand what SPICE is really doing underneath it. The good news is most of the time what you care about is actually the total capacitance at a given node. So as an example, what I often do, let's say that I have one circuit driving another circuit over here. So I have, let's say, one common source driving another common source. From the standpoint of the loading, what I'm probably interested in is the total gate capacitance that I'm going to see from this next transistor. Right? Well, the good news is in order to do that, all you have to look at is the CGG parameter. Because that just tells you if I change the voltage at the gate, what's the total change in charge I get at the gate. Okay? So that's oftentimes what I will use, but obviously, and you can even see it here in fact, when you have things like Miller effect, you have to be a little bit more careful with which direction you're actually looking at what's changing and what is it that you're measuring. Okay? Does this make sense to everybody? Or? So by the way, if you haven't seen it before, go and take a look at this reference. It kind of has a nice short explanation. It's very similar to what I just said. But again, if you're really simulating things, that's how you have to deal with it. So just keep in mind that that's really what's happening under the hood. Okay? Okay, so now here's just sort of really quick review. Hopefully many of you guys, or all of you guys, have seen this at least once, if not several times before. So fine, we have all this nonlinear stuff. Obviously, we don't really want to deal with it with a bunch of complicated equations. We want to know, just roughly speaking, how things are going to behave. Good news is it's not super complicated. Okay, so just maybe to take a quick poll, how many of you guys have seen this stuff before? Okay, anybody not seen it before and want to review? Or, and don't be shy, that's fine. I won't bite your head off or anything like that. Okay, so if you haven't or you need some refresher, go back, take a look at this, make sure you can understand and explain why the caps are what they are in the different regions. I'm not going to spend much time on it. I gave you some sort of example numbers here. This is for an older process. I definitely encourage you, as we're working with our process, go and try and take a look at what some of these rough numbers are, so that, again, when you're trying to do some back-of-the-envelope types of calculations and just see what's either feasible or interesting, you've got kind of those numbers in the back of your head. Okay? So now, to get actually to what Shiva was asking about, if you remember I had mentioned before there's both intrinsic capacitors and extrinsic capacitors. Well, unfortunately, it turns out that generally both in SPICE and in Spectre, if you just instantiate a transistor, so let's say you do drain, gate, source, bulk, and you say W equals 1 micron, L equals, let's say, 90 nanometers. Unfortunately, if you go and you instantiate that transistor, unless somebody has sort of tweaked the SPICE model for you, generally speaking, that device won't include any of the extrinsic capacitance, or that instantiation won't include any of the extrinsic capacitance. Okay? In order to do that, you actually have to add some extra parameters. Now, that's a little bit annoying, but to be fair, SPICE doesn't know how you actually laid the transistor out. So it doesn't know really how much drain stuff is going to be there. So because of that, that's why you basically have to add these parameters in. So again, this is one of the things I'm going to sort of say once, but I'll sort of smack you later if you don't follow it. If you ever simulate a device, put some parasitics in there. Put some drain source parasitics in there. Because as an example, you go and you do your project and you don't put any of those parasitics in, you get these great performance, and I go and look at it and say, oh, that's garbage, that's when I'll smack you. Okay, so just from now on, do it. Okay? So just in case you haven't seen it before, the way you add those parasitics in is with essentially 4 fairly simple parameters. So AS and AD, those stand for the area of either the source or the drain. And PS and PD, those stand for the perimeter of the source or the drain. Okay? And again, just as a reminder, you need both of those components because there's some component of the junction cap that's proportional to the area of that junction. It's kind of, if you look down on the page, basically if you look down into the page, that's the area of that capacitance. And there's also some capacitance that's related to the side walls of those junctions. Right? So that's why you need the perimeter of the device. Now, if you pay attention to sort of the numbers that I've used here in the AS and the AD and the PS and the PD, you'll notice that the perimeters, I'm only actually counting these outside edges. Maybe somebody who didn't take 141, why am I only counting the outside edges? What's magic about the inside edge over there? Maybe somebody who did take 141. What's magic about the inside edge?
You have the channel below the, so these.
Yeah.
It is internal SPICE, etc.
Yeah, so basically, if I draw the side view of the transistor, that inside edge right there is this edge right here, or those two edges, I should say. Those two edges happen to be right next to the intrinsic part of the MOSFET device. They're right next to the channel. So generally speaking, the models actually will include that capacitance automatically. Because no matter what junction area you used, there's going to have to be some cap from that. Okay? So because of that, when you specify the perimeters, basically you don't count the edge that's right next to the gate. Okay? So if we walk through this particular example here, if we say that this, this length of the diffusion is 1 micron, then we'd say that the perimeter is 1 micron from here plus another 1 micron from here, so 2 microns, plus the width of the device. Okay? But notice no gate edge. Yeah?
Is it too much of a problem if we didn't use that in the homework?
Turns out in this homework it won't matter because I didn't ask you anything about it. So, I won't smack you this time. How's that? No, so actually, if you remember in this homework, I only asked about FT, and nicely enough, FT doesn't include anything about this. But next time, do it. Okay. Any kind of questions on this part so far? Okay, so now, as again, hopefully many of you have seen before, if I really had a very long, or really actually very wide transistor, you probably wouldn't want to lay it out just as this one big device like this. Because in fact, if you play one very simple trick, you can actually reduce the capacitance fairly substantially, at least on one of the junctions. Okay? And so the trick you play to do that is you basically say, okay, if I look at this device and I just draw a line across the center, if I then take this whole piece over here and fold it over, what I would basically get is something that looks like what's drawn down there. Okay? Now, why is that advantageous? Well, because what I'm basically doing is I now just have this single area here for that drain junction. It's kind of like I'm folding the thing over and getting the current to flow just into a smaller area where I really want it. What's nice about that is that obviously the area of this is half the area of that, right? So from a parasitic standpoint, I've actually won by almost a factor of 2. Now, I say almost a factor of 2 because indeed the area here is smaller, but of course the perimeter isn't exactly a factor of 2. In fact, when I specify that perimeter, if I was to specify the device this way, I would actually say it's just those 2 microns over there. Because remember, there's the 2 gate edges that are naturally going to come up. Is there a question in the back? Or okay. Okay, so by the way, how many of you guys have seen this before? Okay, good. So now, one other question, maybe just as a reminder. Why do I claim that even if I didn't necessarily care all that much about capacitance, but if I'm building analog circuits, doing this kind of layout is probably actually a good thing to do?
Matching.
Matching. Okay, specifically, what about matching?
The more cells you use, the better matching you're going to have.
Not quite sure about that. There's actually a very specific reason that we talked about in depth, I don't know, a couple weeks ago.
The current directions.
Yeah, there we go. You got it exactly right. So if I use this as my unit cell, I've always got current flowing in both directions. If I do that, I'm guaranteed, no matter how I sort of place that unit cell, I'm never going to mess up the direction. Because it's always got it flowing in both. Now, you can't obviously rotate one versus the other. That will get you wrong. But at least if I always keep the same orientation, meaning, let's say, something like that, as long as I always keep it in the same orientation, and even if I flip it over, I'll still get the same answer from a current standpoint. Okay? So that's exactly why, because of the current directions. Now, one other thing that I need to just briefly mention, because it's a source of great confusion. So, when people do this, sometimes they'll like to refer to that as a 1 micron transistor with an M of 2, meaning that there's 2 parallel 1 micron transistors. And other people like to refer to that as a 2 micron transistor with a number of fingers equal to 2. Okay? So, again, this is a source of almost universal confusion. If you're talking to somebody and they say either one of these 2 things, just make sure, draw the picture and make sure you guys are talking about the same thing. Okay? Usually when they say number of fingers equals 2, this is really what they mean. So they really mean that the width of each individual device is basically the total width divided by the number of fingers. But it's been laid out in a way where those junctions are shared. Okay? People came up with that kind of, let's say, notation or that terminology just to be clear that if I was to do something like this, in Spice, unless I sort of play some tricks, that would literally take two independent devices and just tie all of their terminals together. Okay? So in Spice, if you do that m equals 2, it will just exactly take all of the parasitics from a capacitance standpoint and double them. Okay? Now, in our sort of model, there's nothing explicitly, there's no NF parameter. In other models, you may see that. In ours, there isn't. So when you specify your transistors, particularly in Spice, be careful with how you deal with the multiplicity. Because again, for something like a shared drain device, if you actually told it, if you instantiated the one device as being exactly this, and you say m equals 2, you'll actually have more drain cap than you expected. Right? Because you'll be double counting that piece right there. So just to be clear, if you really did want to specify, let's say exactly this device, what would you type in for the AD parameter? So let's say I wanted to do M1, drain, gate, source, bulk. W is equal to 10 microns. L is equal to whatever, let's say 90 nanometers. What would I type in for the AD parameter, assuming that at the end I'm going to say m equals 2? What would I put there? What do you guys think?
Would it be 1.5 microns?
Say that again?
1.5 microns?
1.5. So that has units of area, by the way, so it would have to be microns squared. So what's the sort of total area that I should get from the entire transistor with both of those fingers there? In other words, what should the total AD actually end up being?
5.
Say that again?
5
5. 5 what?
micron square.
Okay, yeah. So you answered the previous question, but let's maybe do the follow-up question just so that it's clear. So if I looked at this entire device here, and I wanted to know how much area was at the drain, how much area should I count for the entire device at the drain? This is the simple one. This is sort of what's shown on the page here. So
Half a micron times the width.
So again, you answered actually the previous question. So if I'm just looking at this exact device and I wanted to know the area of that piece right there, it's 1 micron times 10 microns, right? That's the entire area of the whole drain. So that's the area I should use for the entire device, right? In other words, that would be 10 microns squared. So now, my claim would be if I specified this device in Spice the way I wrote, I'd have to use 5 microns squared there. Why? Because when I do m equals 2, it'll double the capacitance. So if I want to get the right answer, I have to make sure that I specify half of the area on that drain side for each individual device, so that when I multiply it by 2 at the end, the total area ends up being that. Okay, does this make sense to people, or? Okay, so again, this is something you get a whole lot more practice with as you do your own designs, because this is just going to happen all over the place. The, again, good and bad news is that obviously this comes up all the time. So somebody went into HSpice and actually added a parameter that makes it a little bit easier to deal with all this. There's this thing called ACM, which I think it's something like automatic capacitance model or something like that. Don't remember, but basically if ACM was equal to 3, there's a very nice sort of card you can add to the end of the model or parameter that tells you sort of how it should deal with either is this a shared junction versus a not shared junction. Now, the bad news is we don't have that in our model. But there's many other models that you'll get that will actually have this. So if you see it, that extra parameter that you specify is a so-called geo parameter. So again, when you see a transistor instantiation, you'll get something like M1, drain, gate, source, body, W equals something, L equals something, geo equals something. So in this case, if geo is 0, there's no sharing. If it's 1, which tends to be the most common one, the drain is shared. If it's 2, the source is shared. And if it's 3, then that means both junctions are shared. Okay? So if you had something like a large stack of transistors, you might indeed have something where both junctions are actually shared. Okay? So if you ever see that, that's what that means. Okay. So now that we've kind of spent a lot of time talking about capacitance and all the parasitics and junk like that, now obviously we should kind of get to what we usually mostly care about, which is okay, fine. So from a design standpoint, what's kind of the figure of merit I can use to tell me how fast my device actually is, or really how fast is my device compared to what I'm trying to actually do with it. So as we're going to see again over and over and over again, the metric you generally end up caring the most about is the so-called unity current gain bandwidth, or FT, which is equivalently omega t, just with a factor of 2 pi. Okay? So that particular parameter, again, I'm assuming everybody's seen this, right? Raise your hand if you haven't seen it. Okay, good. Everybody's seen it. So you should know very well that's just GM over CGS plus CGD. If I had a long channel device, you can very quickly work out that FT is just related to the overdrive, or the V star, times mu, divided by the channel length squared. Okay? So, by the way, why is it that it's the channel length squared that comes into the picture for FT, at least with a long channel device? What's happening there? Why is it like doubly bad to have a longer channel device?
The capacitance depends on the length as well as the...
There we go. So, for one thing, the capacitance is proportional to the length. So if I up the length, I'm going to get more cap, right? In other words, CGS and CGD are going to go up. Okay? Not only that, the GM is proportional to 1 over the length, right? Because again, if it's a long channel device, then it's just W over L, mu C ox, etc. So I basically take a double hit. I both get less GM, and I get more capacitance. So that's why, again, in the long channel device, there was this really, really clear motivation to go to as short of a channel as you could. Because the shorter you make that channel, the FT goes up very, very quickly, quadratically, in fact, for the same VOD, which means, of course, for the same V star and for the same current efficiency. Okay, so now, as we said before, unfortunately, we have velocity saturation and things like that. So if you actually look at, for a very short channel device, or really a very high electric field, where the carriers are already going as fast as they possibly can, what's going to happen is that now actually the FT is only dependent on 1 over L. So just to be clear again, out of these two terms, which one sort of fell out of the picture once you get to an extremely velocity saturated device?
GM.
Yeah, GM, right? Because once I'm totally velocity saturated, I can change the length, and it doesn't really matter anymore in terms of how much current I get. Now, obviously, that's not exactly true in any real device, but these are kind of the limits to keep in mind. But really, the key point there is, even if I'm strongly velocity saturated, I have a motivation to really move down in channel length. But also, at least for the long channel device, it's clear that there's sort of this trade-off with my V star, right? So generally what you end up getting, and this is kind of what you'd expect, if I want to get really, really high current efficiency, then what I want to do is I want to operate in threshold. What that unfortunately means is my devices are huge for a given amount of current, so they have huge capacitance, and so the FT I can get is also pretty small. Similarly, if I want to go fast, then what I want to do is actually give myself a nice big VGS minus VT, or similarly a big V star, because I'll get fairly small parasitic capacitance, right? So as you might expect, the trade-off is always going to be how efficient can you make your device from a GM per unit current standpoint versus how fast are you actually trying to make this thing go? Or to say it another way, how small do you want the capacitive parasitics to end up being? Okay, and that's, again, as we had said before, this is really where you see the difference between NMOS and PMOS. So now, as I'd said before, obviously, you want to scale the devices. You get the devices with shorter channel length. You get, really significant gains in the FT. What's actually sort of more important or useful, which is really going to explain how we came up with that V star in the first place, is, well, we've got a trade-off between these two parameters. Makes perfect sense that if I want to know sort of some quote-unquote sweet spot, why don't I just take the product of those two parameters? In other words, why don't I look at the product of FT and GM over ID? Because if I had the perfect device, then this whole product would kind of be infinite, right? But given that I have some non-perfect device, this is kind of a reasonable way of figuring out what's the point at which I'm kind of getting both a nice reasonably high speed and a pretty reasonable current efficiency. Okay, and so if you do that, what you see is actually something very interesting. So if you look back from, let's say, 0.5 micron to 0.35 to 0.25 up to 0.18, you've now done this plot, hopefully, or will be doing this plot for your own 90 nanometer technology. What you'll see is that actually from this figure of merit standpoint, not only is it getting, quite a bit higher, but in fact, you can see the VGS minus VT at which you get this peak figure of merit seems to be converging at something around, this is VGS minus VT, so we have to be a little bit careful with it, but somewhere around 100 to 200 millivolts VGS minus VT, okay? Now this is where actually I sort of pulled off the magic before. Because I just said, well, okay, if I want to get sort of a nice trade-off or a good trade-off between speed and efficiency, I just happen to know that for the technologies that I'm working with, roughly that range of V star, or, well, in this case, I plotted it as VGS minus VT, but fortunately for that small VGS minus VT, it's pretty close to V star. I just happen to know for that range, that usually gives me that nice trade-off point, okay? Now, if you have a specific design problem, obviously you can be more sophisticated than this. You can actually try and figure out, okay, given that the device is going to add some parasitics, what's really the optimal V star for me to use? But by the way, that's usually like, if you're doing that optimization, a lot of the time that's only like 10, 15% of the battle. So that's why back when we did that other, that previous example, I basically just said, okay, I'm just going to pick a V star of about 200 millivolts. Because I know that that usually is about the right spot to be in. Again, obviously in any specific design it may move around, but kind of as I said here in the slide, if you're in doubt, choose V star of about 200 millivolts. Because it just so happens that for most technologies that you're going to deal with, that's a kind of nice spot to be in from the standpoint of trading between current efficiency and how much parasitics your device is actually going to introduce. Okay? So just to be sort of sure that all this is really clear, let's say that I told you that let's say we're working in this 0.18 micron technology. And let's say I told you I want to do something with a gain bandwidth of, let's say, let's say I want, let's say 500 megahertz or something like that. Okay? So based on everything we've talked about so far, what kind of V star do you think you'd end up choosing? At least which direction do you want to push that? So by the way, 200 millivolts is like the nominal, if you do nothing, then you should just say 200 millivolts. So, that's... So let's say I want to gain unity gain bandwidth of 500 megahertz, and I'm in this 0.18 micron technology here. Okay. So just maybe as a point of notice, at 200 millivolts V star, your FT is about 45 gigahertz. So what kind of V star do you think you're going to want to use for this particular amplifier? Let's see if we can get anybody to even give a direction. So who wants to go that way? In other words, higher VGS minus VT. Anybody? Okay. Anybody want to go the other way? Lower VGS minus? Okay, there we go. Why?
More efficient.
Yeah, it's more efficient, right? Now, what's going to stop me from taking this all the way, other than, I hit sub-threshold? Why might I not want to make this like 0 VGS minus VT? What could I eventually potentially run into?
Too slow.
Say that again?
It'd be too slow.
Yeah, so you're right, it'll be too slow, but what does that really mean? From the standpoint of my design, what does that kind of mean? What's the penalty I would pay if I use too small of a V star?
I need bigger area for same current.
Okay, I need bigger area for the same current. I'm in, let's say, in 0.18 or whatever, so maybe area is not the number one thing I care about, because usually the caps are huge in comparison anyways. But that's true. What's maybe more important? Say that again?
Variation.
No, actually, well, maybe. Bigger devices in some senses are better, but you're right, I'm in subthreshold, but there's actually something even much more direct.
You can't swing.
Say that again?
The swing will be lowered.
No, actually the swing's better, so unfortunately that's the other way. What else is going to happen? So, by the way, let me give you a specific number. Let's say I've told you that I'm driving 100 femtofarads of capacitance. And let's say that with a V star of, 60 millivolts, I'm going to have a 2 millimeter wide device over here.
Your parasitics will become comparable to your load.
Bingo. The problem is if I push V star too small, the parasitics from my own stupid device are going to be huge in comparison to what I was trying to drive in the first place, right? So that's why at some point, if I was actually to do a plot of, let's say, power of my circuit versus V star, what you'd see is something that looks like that. Okay? So basically there's some region around here where the device is kind of reasonably small in comparison to the load you're driving. And so any V star kind of in that range makes sense. If you make the V star too big, yeah, your device is really fast, but you have really crappy efficiency, so you're just burning more power than you need to. Make your V star too small, then you get this silly situation like this, where the parasitics of the device are just ginormous in comparison to anything that you're actually trying to drive. Okay? So again, that's really why, by the way, this other, this composite metric that we were talking about, that's another reason why, you see these kind of flat, nice trade-off point there. Just so happens that point usually corresponds pretty well with about where you want to be from the standpoint of minimizing power. Okay? It's not a universal truth, so you should take that as kind of an intuitive, slightly hand-wavy kind of thing. But that's just another way of saying why is it that this is roughly the kind of region you're sitting in. Okay? Obviously, if you're going to be doing some super high-speed design, you're going to have to move up off of that point simply because that's the only way you can actually get the transistors to basically hit that kind of speed. Or in other words, make sure that their parasitics aren't huge. Or if you're doing some really, really low speed design, then indeed you really want to push down as close to the subthreshold as you're kind of willing to actually go. This make sense to everybody here? Okay, so what I basically did here is just kind of quickly summarize the design procedure that we talked about earlier. I wanted to put this here because, again, you're going to be doing this kind of over and over and over again. So I don't think I need to walk through it again one more time. It's here. Go back, take a look at it. You'll get very familiar with it. We'll be using it a whole bunch more times. So any last questions on this before we sort of move on to the next major topic? No. Okay, great. So let's just go ahead and start on noise, and we'll pick up with that in the lecture later this afternoon. So, now that we've sort of talked a little bit about how we're going to model the devices, how we're going to deal with all the junk that is frankly painful to deal with, but hopefully now we've got a reasonable way to do that, our next step is really we need to look a little bit at noise. Okay? Now, the first question obviously is, why the heck am I going to be spending actually probably about 3 or 4 lectures just talking about noise? Well, so it turns out noise is actually pretty darn important. And in fact, in many applications that you might be working on, it's going to turn out that noise is very directly going to set how much power your circuit has to dissipate. And now, the intuitive reason for that is perhaps obvious, but let's maybe walk through it really quickly, and we'll, by the next couple lectures, we'll be able to derive exactly why this happens. But basically, if you kind of think about it, any noise I have in my circuit is really going to set how small of a signal can I actually deal with, or how small of a signal can I actually measure. Okay? And in general, the way you'd like to think about that is something usually referred to as signal-to-noise ratio. That just means how big is the signal that is what I really want. Let's say the signal coming off my capacitive sensor in my iPhone, or my accelerometer in the Wii, or whatever it is. How big is that compared to just the fundamental noise coming from my circuit? Okay? So again, as we're going to see very quickly, the amount of sort of swing or the amount of voltage I actually have in my signal is usually directly related to the supply, because that just sort of sets how much swing I can actually use. So my so-called signal power is usually related to the supply voltage squared. Okay? And as we'll be seeing hopefully later this afternoon, the amount of noise you're going to get from most of the circuits we're going to talk about, the amount of noise power, is going to be related to kT over C, okay, where C is the capacitance you're driving in your circuit. Okay? And kT, by the way, or kB is Boltzmann constant, T is temperature. Again, we'll see where this comes from in 1 second. Now, why is this important? Well, we can actually already do something like a very quick calculation. Okay? So let's say that I want to basically get a circuit that's twice as good from the standpoint of the smallest signal it can deal with. Okay? So let's say in your radio or something you want to go like twice as far away or something like that. Okay? So in an analog circuit, we can actually figure out very quickly, and again we'll go through this in a second, that in order to do that, I'm actually going to have to burn 4 times as much power. Okay? Why is that? Well, basically, if I would need to have a smaller noise to deal with that smaller signal, I'm going to have to increase that capacitance. When I increase that capacitance, if I want to get the same speed, I obviously have to spend more power in my amplifier to actually drive that capacitance, right? Now, why is it as a factor of 4 versus a factor of 2? Again, I'll get into in 1 second. But this is actually one very sort of critical thing to keep in mind in terms of how analog circuits scale versus how digital circuits scale. Okay, because in analog, as I just said, if I want to get basically a factor of 2 more precise, that's going to cost me a factor of 4 in power. By the way, in digital, if I wanted to get a factor of 2 more precise, what do? How do I change what I build? Yeah, I add 1 bit, right? Sounds trivial. So instead of building, let's say, a 32-bit adder, I build a 33-bit adder. Big whoop, right? Now, obviously, things are not quite that straightforward, but that's, in some senses, that's really what it gets down to. Okay, and so actually, as we go through, we'll give you some example numbers. What I'd encourage you is afterwards, go home, try and calculate how many bits can you actually get out of an analog circuit with, let's say, a supply voltage of 1 volt and a capacitance of even, let's say, 10 nanofarads, which, by the way, is huge for an on-chip cap. Okay? Just based on these numbers that, again, we'll go through, just see how many bits can you actually get from an analog circuit. And I'll give you a hint. It won't be anywhere near your 32-bit microprocessor. Okay? It'll be actually quite a bit smaller than that. Okay? The bottom line is that we have to talk a little bit about noise, because if we don't understand noise, we're not really going to know how to build circuits in analog that are going to have to be able to have any kind of precision associated with them. That'll be able to deal with the relatively small signals that often are the reason you're building analog in the first place. Okay? Now, I should be careful to sort of define one thing here when I say noise. So, oftentimes when I say noise, I'm guilty of this. I usually mean anything that I don't want, meaning any kind of junk that wasn't what I wanted. So, in most of this class, that's not what noise really means. Okay, so in most of this class, what noise really means is basically fundamental noise coming from variations inside of the devices. Okay? Or meaning thermal noise, which again, I'll define what I mean by that in a second. But what I really mean by noise is things that you can't actually predict ahead of time, meaning you don't know what the value of that signal is going to be. So it's truly random. For all of the other stuff that's signals that you don't care about, that's really technically should be called interference. Okay? So as an example, something like 60 hertz hum, or let's say some digital gate is switching and that causes a glitch at the input of your amplifier. All of that technically is interference. Okay? Because that's all, in principle, I should know exactly what it is. Or I could calculate exactly what it should be. So again, in most of this class, we're going to be spending our time down here, certainly for the next couple of weeks. But don't forget about this interference stuff. Okay? Because oftentimes that can be just as important, if not even more, than the fundamental noise sources. Okay, so stuff like, again, 60 hertz or just some digital gate somewhere, all of that is actually quite important as well. If we have some time, we'll talk some more about it later on towards the end of the class. But for now, since I'm assuming many of you have not seen sort of thermal noise before, we're going to spend some time just focusing on that. Okay? So, what is this noise that I'm talking about? Or where is it kind of coming from? Well, and hopefully maybe one of you guys have actually tried this experiment once. So if I take any amplifier or really any circuit, let's say I take the amplifier and I just put ground at its input. And I measure its output with, the most precise thing that anyone has ever built. What you're always going to see is, rather than getting exactly 0 volts at the output, you're going to see these weird, squiggly stuff. Right? Just random junk kind of all over or all around that nominal 0 point. Okay? Turns out that's really fundamental. Where that noise comes from just has to do with the fact that I have a bunch of electrons. Even though those electrons maybe on average are not supposed to be moving, each individual one is actually kind of bouncing around inside of the materials that make up this amplifier. And so as they randomly bounce around and happen to either, let's say, go in one particular direction, or let's say hit my electrode or whatever it is, I measure a little blip of voltage. And now, on average, clearly there shouldn't be anything kind of coming out of the amplifier. But because of these random little variations, I'm going to see these random variations in the output as well. Now, there's one sort of really critical point that, especially if you haven't dealt with noise before, kind of gets people tripped up a little bit. So the critical point here is noise is truly random. Okay? And so when I say it's random, what that means is you cannot ask a question like, what is the value of the noise at time blah? Okay? The answer is, I have no idea. It's random. Okay? So the only things that you can characterize with random processes, like noise, is basically statistical characteristics. So all you can say is, what's, let's say, either the mean or the distribution of the noise, or what's like the spectrum, meaning what's the frequency characteristics of the noise or the dynamics of the noise. But you can't ask, what is the value of the noise? Because it's sort of by definition not a valid question. Okay? So from now on, actually, when we talk about noise in circuits, and I'll sort of point out a couple times how this comes into the picture. When we talk about noise in circuits, you're going to have to keep in mind that what you're actually calculating is statistical properties and not the value of the noise. Okay? Does this make sense to everybody? Or? Okay, so I think we're basically out of time for this lecture. Hopefully I'll see some of you guys later on Thursday, and if not, or excuse me, today, and hopefully you guys will watch that later on in the video. So see you guys later.